All right, guys, and moving on to the second half of our notes here in 2.6, we're now moving on to our fourth type of transformation right here, and that's what's called a horizontal reflection. So the one we just finished up a few slides ago was a vertical reflection. That's what happens when there's a negative out in front of the f of x or g of x or whatever it is. But now with a horizontal reflection, you'll notice there's still a negative, but this time it's going to be inside the parentheses. So, kind of like a horizontal transformation was a number added or subtracted inside the parentheses. A horizontal reflection is what happens when there's a negative sign, but again, it's inside the parentheses. So if you put a negative inside the parentheses on your x, that reflects the graph of the original function f of x over the y-axis. Okay, so now instead of a kind of a vertical reflection like we did before over the x-axis, now what we're going to be doing in this section is going horizontally around the y-axis, like so. So let's see what that one looks like in action. Okay, so here again is that same linear function that we dealt with before, so we'll go ahead and graph that one out. Negative 2/3 x plus 4, just like last time, had a y-intercept of 4 and a slope of down 2 and right 3. So I'll try to do the same 4 points that I did before, down 2, right 3. And I tell you what, actually I'm going to do one more here. From my y-intercept, I'm going to reverse field now and go up 2 and left 3 and get one more point there. There's a reason why I wanted that point here for this example, and I think you'll see why in just a second. So here we go. That's a pretty straight line. All right, so that's what our original graph looks like. Our job now is to graph f of the opposite of x. So, back to the previous slide, what that does to put a negative inside the parenthesis is reflect your graph over the y-axis. We're now spinning the graph around this way with the y-axis going right down the center. So, a few examples ago, when we did a vertical switch right there, every point that was above the y-axis now got moved below. Every point that was below the x-axis now got moved up above. This time we're doing something different. This time we're going horizontally around the y-axis. So every point that is on the y-axis, like this one right here, stays put. Every point that is to the right of the y-axis, like this point here, is now going to flip over the y-axis, and its x-coordinate is going to change from positive 3 to negative 3. This point here had an x-coordinate of 6, so we're now moving that to an x-coordinate of negative 6. This point right here had an x-coordinate of 9, I believe. It's now going to be negative 9. And this is the point that I wanted to talk about here. This point on the original graph had an x-coordinate of negative 3, so we take the opposite of that, and it now has an x-coordinate of positive 3. So now I've got 5 collinear points in red. We'll go ahead and we will draw the line between them all, and that is the graph in red of y equals f of the opposite of x. Putting a negative on the x in the parentheses shifts the graph, or I should say reflects the graph over the y-axis. That's a horizontal reflection. Let's do one more example of that. Now this is another function, kind of meant just to scare you a little bit right here. G of x is equal to, you guys don't even know what that is. That is a cursive L and then a letter N, natural log of x. This is something we're going to be learning about, if I had to guess, late February or early March. Now again, it's not important for you guys to know what that graph looks like. You just need to trust me right now. It passes through the point 1, 0, and this graph has a vertical asymptote there at the x-axis, and it just takes this nice gentle curve that looks something like that. So this would be something that grows very, very quickly at first, and then over time it continues to grow, but it levels out. You might be talking about maybe the population of a city. When it was first new, it probably grew very quickly, and then over time that rate of growth slows. But you know what? That has nothing to do with this section, guys. That graph in blue would be given to you. Our job is to come up with the graph of y equals not g of x, but g of the opposite of x. So, because there's a negative on the x inside the parenthesis, this is another horizontal reflection. We're spinning things around the y-axis. So I started with the original point of 1, 0. That now flips over to the point negative 1, 0. And we still have this same vertical asymptote here at the y-axis, but this one is now curving and looking something like that. So I didn't draw that perfectly correct, guys, but it's pretty close. That in red would be the graph of y equals g of the opposite of x. It's just a mirror reflection of the original blue graph of g of x flipping over the y-axis. Okay, so that is now 4 of the types of transformations we need to learn in this section. One last one before we're done. Vertical stretching or compressing. And this is one we're going to be using a lot this year. There was supposed to be a dot right there and it didn't quite work out. That's multiplication. If you're taking a multiplied by a function, f of x, 2 rules here, guys. If a is greater than 1, okay, the most common values you're going to see there would be 2 or 3. But if a is greater than 1, you're multiplying the value of your function by 2 or 3 or 4. What that does is it takes the graph of the original function, f of x, and it stretches it vertically by a factor of a. So it's basically taking a graph that did something like this and it is now stretching it and making it even taller than it was before. That's what we mean by stretching something vertically. But the second half of this happens right here if a is smaller than 1. So your common values you might see there would be something like 1/2 or 1/3. We really should be saying if the absolute value of a is less than 1. But if that happens, if you're multiplying your function by a number like 1/2 or 1/3, then your graph of x is not being stretched, it's being compressed vertically by a factor of a. So let's see if I can do a little trick on the smartboard software right here. If you were to come up with, let's just say like a normal person right here, a stick figure like that, let's see what Mr. Fontana can do with this here, guys. If I tap that twice, let's see, I think I can, let's do an infinite cloner. Okay, here it is, everybody. There's 3 of you. Good job. All right, so the first graph we have here, this one, we'll call this graph A, that is what you look like normally. But if you've ever gone to like a fun house at Cornfest or some other carnival right there, you sometimes see mirrors there. And sometimes what those mirrors can do is they can distort the way that a graph originally looks. And so what I'm talking about initially here would be the idea of stretching something vertically. What I've drawn right here is an example of this concept, guys. Something is now taller than it was originally. So I'll call this graph B. Now you got to be careful here because at first glance, if you don't look carefully, it looks like graph B is skinnier than graph A was. That's not actually the case. It's really just taller, yet something being taller gives it the illusion of being skinnier. But graph B has been stretched vertically, so that is what we call a vertical stretch. And in our third case right over here, I'll call this C in just a second, what would happen here is that your graph is being compressed vertically. This is what C, graph C might look like. And so this piece of info right here, that is what vertical compression looks like. Again, now the graph of C looks wider, it looks fatter than the graph of A, but really it's the same width, it's just been shortened vertically. Kind of like that goofy mirror in the funhouse makes you look really fat when in actuality it's just making you look short. Okay, and looking fat is just an optical illusion. Yeah, let's go with that. All right, so that's what's going on with vertical stretching and compressing. So, a couple quick examples and then we're done with this one. Now again, the original graph will be given to you, so don't worry about not knowing what this is. This parabola is actually one of the first things that we're going to learn how to do of nonlinear graphs, and we're going to be getting to that really within about a month or so. So that is the graph right there of h of x. We're going to come up with 2 variations. The first one we're going to do in red is the graph of 2 times h of x. So every y value on that graph is now going to get multiplied by a factor of 2. Now the first thing I want to talk about is this point right here at the origin. It initially had a y coordinate of 0, and we're now multiplying all of those y coordinates in h of x times 2. Well, 2 times 0 is still 0. So this point, which was on the x-axis, isn't moving at all. But every other point that was on the original graph, like this one right here, is now getting stretched up to be about twice as far away from the x-axis as it was. I'm moving all these points up. So what that's doing now is it's making this graph taller than it was before, which gives it the illusion of being skinnier. So that would be the graph of y equals 2h of x. And then in green here, I've asked you to do another one just on the same graph right here to save ourselves a little bit of room here. Let's take a look here, guys. The graph of 1/4 h of x. Similar thing, there's an a value being multiplied by h of x out in front, but in this case, our a value is 1/4. 1/4 being less than 1 means that we're multiplying our y values by 1/4, which actually makes them smaller than they initially were. So again, guys, that initial y coordinate of 0 gets multiplied by 1/4, it's still 0. But now, all of those, oh boy, the red dots on the blue curve now get smushed back down, that's a highly technical term, closer to the x-axis than they were, and that is going to make this green graph a lot shorter than it was. And it gives it the appearance of being wider, but it's really just being pushed down. The blue graph is being smushed that way. And so that's what our graph of 1/4 h of x is going to look like there. Okay, so that's kind of a sense there, everybody, of what do we have here? This was vertical stretching because our a value was greater than 1. Here a was equal to 2, and that means that we're stretching the graph out this way. But then in the second example right here, we had an a value equal to 1/4. And since that's less than 1, that means that we're actually compressing the graph inward, something like that. That one's going to take a little bit of getting used to, but that's one that we use a lot during the course of the year, so good news, you guys will get to practice it plenty. Okay, guys, that's a wrap on our notes for 2.6. Let's give that homework a try and see how we do on that. Good luck.